Welcome to this explainer. Today we're going to do something pretty incredible. We're going to take what honestly might look like a totally dry list of algebraic formulas, and we're going to transform them into a dynamic, immensely powerful toolkit. If you're prepping for a massive competitive exam, like the IIT JEE, you already know that time and efficiency are literally everything. So today, we're architecting a foundation in sequences and series that doesn't just help you memorize stuff, but actually gives you a real mathematical superpower.
But first, picture this. You're staring down a brutal exam question. You're asked to find the absolute maximum or minimum limit of an equation. Your first instinct is probably going to be to pull out the heavy, time-consuming calculus, right? Derivatives, critical points, the whole shebang. But what if I told you there's a way to find those exact maximum limits without using calculus at all? The secret to solving this seemingly impossible problem actually lies in the simple, everyday building blocks of mathematical patterns.
Okay, let's dive right into this. Here's our roadmap for today. Number 1, we'll review patterns, specifically sequences and series. 2, stepping up with arithmetic progressions. 3, multiplying fast with geometric progressions. 4, bridging gaps with means. And finally, 5, we'll reveal the AMGM superpower.
Let's start with Section 1, Patterns, Sequences, and Series.
Let's just make sure our definitions are crystal clear here. A sequence is the ordered list itself. It's governed by a strict rule, like 2, 4, 6, 8. A series, on the other hand, is simply what happens when you sum all those terms up. So the sequence is the list, and the series is the sum. Pretty straightforward.
Moving right along to Section 2, Stepping Up, Arithmetic Progressions. Think of an arithmetic progression, or an AP, like climbing a perfectly spaced set of stairs. The core engine running the whole thing is the constant difference, which we call D. No matter where you are on that staircase, subtracting the previous term always gives you D. And this shapes the sequence's general form, right? You start with A, you step up to A plus D, then A plus 2D, and so on.
And because this march upward is just so incredibly predictable, we can essentially teleport to any step on the staircase without having to climb all the way from the very bottom. This beautiful, absolutely critical formula lets us find the nth term of an AP instantly. The nth term equals the first term A, plus the number of steps we want to take, which is n minus 1, multiplied by the size of that step, D.
Let's actually see this in action. Suppose you need to find the 20th term of the AP, 3, 7, 11, 15. Step 1, we identify our starting point. A equals 3. Our common difference D is 4, because 7 minus 3 is 4. Step 2, we just plug this straight into our formula. We want the 20th term, so it's 3 plus 19 times 4. Step 3, calculate it out, and we get 79. It's simple, it's fast, and it's elegant. Oh, and as a quick aside, if you ever need to sum up all these terms to create an arithmetic series, you'd use the sum formula, n over 2 times the quantity 2a plus n minus 1 times d.
All right, Section 3, Multiplying Fast, Geometric Progressions.
Let's pit the AP right up against the geometric progression, or GP, to really see the difference here. While the AP relies on additive constant differences, the GP relies entirely on multiplication. It uses a constant ratio, R. Because it multiplies, the sequence morphs into exponential growth. A, then A times R squared, A times R cubed. It behaves a lot like a viral rumor, just spreading faster and faster with every single step.
And just like our AP, the GP has a master key for finding any term in the sequence. The nth term of a GP equals A multiplied by R to the power of n minus 1. It's also really good to know that if you're ever summing an infinite GP, and your ratio R is a fraction between -1 and 1, that infinite series actually converges perfectly to a neat little formula, A divided by 1 minus R.
To really grasp how ridiculously fast a GP scales, let's just find the 6th term of the sequence 2, 6, 18, 54. Step 1, identify the first term. A equals 2. Our constant ratio R is 3, because 6 divided by 2 is 3. Step 2, plug it into the formula. The 6th term is 2 times 3 to the power of 5. Step 3, well, 3 to the 5th power is 243. Multiply that by 2, and you get 486. See that? By just the 6th step, these numbers are getting massive.
Which brings us to Section 4, Bridging Gaps with Means.
So what is a mean in this context? It's essentially a mathematical bridge inserted between two numbers so that they form a completely valid sequence.
The arithmetic mean creates an AP using a plus b divided by 2. For example, the AM between 10 and 20 is 15. That gives us a perfect AP, 10, 15, 20. Conversely, the geometric mean creates a GP using the square root of a times b. The GM between 4 and 25 is the square root of 100, which is 10. And boom, you have a perfect GP. 4, 10, 25.
And this brilliantly illustrates how we can scale this whole concept up. What if you need to insert multiple means? Let's say we want to insert 3 arithmetic means between 5 and 25. Step 1, realize you now have 5 total terms, your 2 endpoints plus the 3 new means. To find our new constant difference, d, we take the gap between the numbers, b minus a, and divide it by n plus 1. Step 2, that's 25 minus 5, which is 20, divided by 4, so our step size d is 5. Step 3, just build out the sequence. 5, then 10, 15, 20, and finally 25. Your 3 means are 10, 15, and 20. Really, it's just a matter of finding that new constant difference.
And finally, the big one, Section 5, the AMGM superpower.
Here it is, the AMG inequality. For literally any positive numbers, the arithmetic mean is always greater than or equal to the geometric mean. I'm going to repeat that because it is absolutely crucial. A plus b over 2 will always be greater than or equal to the square root of a times b.
When you compare the two of them, the arithmetic mean is inherently going to stand taller than the geometric mean. Addition, when you average it out, outpaces the average product. They only ever level out and achieve true equality when your two variables, a and b, are the exact same number. You've got to keep that specific condition of equality in your mind.
But, why does this actually work? Let's prove it logically right now so you don't just memorize it, you actually internalize it. Step 1, we start with the universal truth. Any real number squared is positive, meaning it's greater than or equal to 0. So the square of the quantity root a minus root b has to be greater than or equal to 0. Step 2, we simply expand that binomial. That gives us a plus b minus 2 root ab is greater than or equal to 0. Step 3, just rearrange it. Move 2 root ab to the other side, divide by 2, and boom, there it is. A plus b over 2 is greater than or equal to the square root of ab. The logic is absolutely flawless.
So let's circle back and answer that exact question we hooked you with at the very beginning of this explainer. How do we bypass calculus to find limits? Application 1, finding a minimum value. Suppose you absolutely need to find the minimum of x plus 1 over x for positive values of x. Let's just treat x as our a and 1 over x as our b. Plug them straight into the AMGM inequality. The left side is x plus 1 over x divided by 2. The right side is the square root of x times 1 over x. Notice what happens on the right side there. The x's cancel out perfectly to leave the square root of 1, which is literally just 1. Multiply both sides by 2, and you instantly prove that x plus 1 over x must be greater than or equal to 2. The absolute minimum is 2, and it happens when a equals b, meaning when x equals 1. No derivatives required. How cool is that?
The flip side of this application is honestly just as powerful, finding a maximum product. Let's say you have a fixed sum. For example, a plus b equals 20, and you need to maximize the product ab. We already know from earlier that the maximum potential is reached when the two quantities are exactly equal, so we force equality. We set a equal to b. If a plus b is 20, well then, both of them must be 10. The maximum product is simply 10 times 10, which gives us 100. It is incredibly satisfying to cut through complex algebra that fast.
To wrap things up, here is a complete toolkit of exactly what we've built today. Arithmetic progressions rely on a constant difference. Geometric progressions rely on a constant ratio. The arithmetic mean bridges gaps with addition divided by 2, while the geometric mean bridges with the square root of a product. And the crown jewel of it all, the AMGM inequality. Use it relentlessly for minimum and maximum limit problems. And always remember, equality holds true if and only if the quantities are exactly equal.
We've seen how transforming a dry list of numbers into a structured, powerful understanding of sequences and means unlocks an incredible shortcut for competitive math. But honestly, it leaves us with a totally fascinating thought. If simple, fundamental patterns of addition and multiplication dictate the absolute limits and boundaries of these complex algebraic equations, what other physical boundaries of our entire universe are currently hiding within mathematical sequences, just waiting to be calculated? Thanks for joining me on this explainer today. Keep your eyes on the patterns and keep learning.